Let's talk about the syllabus. So what we're going to do is start off with basic concepts of linear system theory with applications and numerical methods. Then what we're going to do after this is modeling and design of linear controllers using state space methods, and also apply this to independent joint control. Controllability, observability, and realization of dynamic feedback controllers. So first of all, we need to learn what does it mean for a system to be controllable? What does it mean for a system to be observable? What does it mean for a realization to be minimal and things like that? We'll learn some basic concepts from optimal control. The way this is written, this is not in chronological order. So we might cover some topics before others. We learn some basic concepts of optimal control, where we learn things like LQR and LQG controllers. We learn some basic concepts of Lyapunov stability theory and frequency domain methods. We'll also go into that towards the end of the course. Nonlinear control and model predictive control if time permits. That's going to be the course outline. This might seem innocent and not very challenging, but this is very heavy outline. And you're going to soon see once I start deriving things and start working with things. In order to understand some of the results I'm going to present, I would have to prove them as well for you. Because in the proof, sometimes you understand there is a deep understanding of what is going on with the result. And we're going to have that. Let's start with the first lecture. If you look at the structure of a control system, there is this overall feedback structure that is similar to many systems. Here, let's consider the cruise control of a car. So in the cruise control of a car, of course, you have some sensors that measure the speed of the car, right? So your speedometer, for example, will tell you the actual speed of the car. There's a desired speed that you will set. What is it? They have a little button. You press that and put the lever down, and the speed is set, right? Whatever speed you're at, and the cruise control is set. So that's a desired speed. And then as the car travels on the road, there will be, all kinds of challenges. Maybe you brake somewhere, and it breaks. The cruise control breaks if it ends the loop, right? But let's say if you were just driving and didn't brake, there might be a hill or there might be a slope, and it adjusts accordingly. So if the actual speed is not according to the desired speed, even if it is equal to, it goes to a comparison block that compares the two. And if there's an error, that error goes to the decision controller. That comes up with control laws that can drive that error to zero. Purpose of the controller is to ensure that you have desired behavior. And it tries to drive that error to zero, and that a control signal is generated that when applied to the actual system, which is the car, if that logic is applied to the car, the error would go to zero. How control signals are applied to systems are through actuators. So an actuator is basically a component through which the control system interacts with its environment. So for example, in your car, there is something called the cruise control actuator.